going to be working with kinetic molecular theory. And so we are in your packet right now and looking at page 1. The kinetic molecular theory of gases can be used to explain why gases behave the way they do. So there's 7 things that we have to focus on as we are going through and talking about gases. So we're going to use some abbreviations and these little clues to kind of help us go through and do stuff. The first thing you always want to look at is evaluating a situation. And evaluating the situation, you're always going to decide what kind of container or system that you have. So you can either be open or closed, which means that gases can obviously move in or out, or you're going to have a flexible or inflexible system, and that's going to affect your pressure versus your volume as we go through and do things. N is going to stand for moles. T is going to be for temperature, but temperature only changes if we change it. It has to be the start of a situation. It's not going to change as in a result of other things when we're talking about ideal gases, and we'll talk more about that later. So we have kinetic energy, which is KE, and remember that temperature and kinetic energy are directly related since they're the definition of each other. And then we have C for collisions and P for pressure. And remember, pressure is going to be caused by the collisions of molecules with the sides of the container. And then we have V for volume. So like I said, the number one thing you're going to do is pick container type. And then from these, you don't just list them. You have to find what the start is. So find the start. And you'll understand in a second when we do an example about what I kind of mean. And often with pressure, we are going to end up having to write pressure inequalities. So we'll come back and look at that in a minute as well. Alright, some relationship that exists between variables. Collisions and pressure are directly related since the definition of pressure has to do with collisions. So if collisions go up, pressure goes up. If collisions go down, pressure goes down. Next we have temperature. Temperature and kinetic energy, I already mentioned, they are directly related as well, since temperature, the definition of temperature is the average kinetic energy of your individual molecules. So as one goes up, the other goes up, or down, and likewise. Okay, so here's where it gets a little bit different. If collisions change, so that's your number of collisions, then either pressure or volume will change depending on the type of container, and this should make sense. If we have a closed container that is inflexible, so closed meaning air can't come in and out, or gases can't go in and out, and inflexible meaning the volume cannot change. Then when the collisions go up, obviously the pressure is going to have to go up as well. The volume is staying constant because it is an inflexible container. It cannot change. And then N is going to stay the same because it's a closed container. Whereas if this was an open container, then the molecules could leave, and temperature and kinetic energy are going to stay the same. But if we have a closed flexible container, as your collisions go up, your pressure would go up, but the pressure inside would be greater than the pressure outside. Since this is a flexible container, then the pressure on the inside pushes and actually changes the volume. And it's going to stop pushing when the internal pressure equals the external pressure, or P in equals P out. And since it's still closed, we're going to have N stay the same, and temperature and kinetic energy are going to stay the same. So the difference between these two, in a flexible container, your pressure goes up, but only momentarily. Overall, your pressure will go back to being what it was before, because it is going to push on the container in order to equal out the pressure. Here's something else. In an open container, the number of moles can change, which would then change the situation and the variable. So if the collisions go up and the pressure is going up inside, if it's open, then it can push molecules out, push N out, and change the situation. Okay, so if a container is flexible, its volume can change. While an inflexible container, the volume remains constant, unless, of course, you reach the capacity of the container where it ends up kind of like blowing up or can't go anymore. So let's determine which of these following are flexible or inflexible containers. So I'm going to give you a minute here to look at this and try and make your own decision. So you decide whether a balloon is flexible or inflexible. And in our world, a balloon is going to be 100% flexible until the point where it would break or burst. Okay, what about an aerosol can? hopefully everybody said inflexible, to the point, of course, where you could blow it up, though, and reach its capacity. Now think about a syringe for a minute. A lot of people like to think that syringes are inflexible because they have a hard outer shell. They're really flexible containers because in a syringe, you use the plunger to go back and forth, and you get to change the volume. Okay, so if the volume can change, that's our definition of flexible. All right, so let's put all of this together and see if we can't see how this actually affects our examples that we are doing. So we're going to go back up to the top here as we work, and we're going to use all these variables for the new situation that we are looking at. And so first, remember, we want to do container type. So let's go down here and read our situation. Adding more molecules to the same amount of space. 2 aerosol cans. The first contains fewer molecules. So these are our pictures. So we have less molecules, more molecules, same amount of space. So space, you should think of volume. Let's go back to see what we do first. We have to do container type. Is it open or closed, and flexible or inflexible? Now this container could be opened, but the containers are just sitting there. There isn't somebody pushing down on the container and opening it. So we are starting with a closed container. And our aerosol can is inflexible. Now we have to see what changed first. So we say we add more molecules. So look up here and see which one of these things is most similar to molecules. Which variable would be the best choice if we want to talk about molecules? Hopefully you said moles, or N. We're going to use abbreviations as we go through and do this. You could write paragraphs and sentences. I like to do little abbreviations with a combo of some sentences in between. So our start is going to be that we added more molecules, so N goes up. Then you have to think, if N goes up, what is the next thing to happen? Okay? And as we go here, lots of kids like to jump and just say pressure goes up. But pressure cannot be the thing to change first. So when we look at this, it's caused by collisions. So in order for pressure to go up, collisions has to go up first. So if we have more molecules, then we're going to have more collisions. And if we have more collisions, then we are going to have a higher pressure. Now at this point, whenever we talk about pressure, we want to do some pressure inequalities. So right now, if the pressure went up inside the can, then the pressure inside the can is greater than the pressure outside the can. Sometimes we just write that, and it has no other impact, like nothing else can change. So right now, it's just a fact that inside now the pressure is greater than it was on the outside when we originally started. This demo is pretty much done. That's all we did was add more, nothing else really changed. So now we have to account for all 7 variables, and right now we only have 4 of them. So we need to go back and look at the other variables and see whether we forgot about them or they just don't change. They maybe just stay constant. So here we have temperature. It only changes if we change it, and kinetic energy and volume. Those are the 3 things that we are missing. The volume in here, it told us that it had the same amount of space. So volume is the same. And then since temperature and kinetic energy, we didn't change it, then all of those are actually going to stay the same during our demo. So this is a pretty basic start to our kinetic molecular theory. And we're going to skip over some right now. Don't do these tonight. You're going to work on them tomorrow in class. We're going to skip down to a little bit of a harder one, a little bit more complicated, and we'll see what happens with this one. So we're going to work on number 5 here for a minute. It says, why does a balloon expand when it is heated? Okay, so remember, we have to go back to our variables and start at the beginning. So what's the first thing we have to do? We have to decide our container type, open or closed, and flexible or inflexible. So a balloon is closed, and a balloon is flexible. So let's go back and add that in there. Now the next thing we have to do is look at our variables and find the start. It says, why does it expand when it is heated? Okay, so we have to think, what does heat have to do with our other variables? Which one is going to be our start? So hopefully everybody picked temperature to be our start. And so if temperature changes, then remember kinetic energy has to change right away as well, because those two are directly related. So temperature went up, so did our kinetic energy. If your kinetic energy went up and you are moving faster, what's going to change next? Take a look here. What do you think? Collisions. You are going to hit more often. And if you hit more often, then your pressure is going to go up because pressure is defined by collisions. Okay. So we've got increase in collisions and then an increase in pressure. Now remember, whenever we say pressure, we want to add a pressure inequality. So by saying the pressure has gone up, the pressure inside the balloon is now greater than the pressure outside the balloon. Now before, when we had an inflexible container, we stopped here because nothing else can change. But in a flexible container, volume can change. So when the pressure inside is greater than the pressure outside, it is going to push on the sides of the balloon and expand until the pressure inside the balloon is going to be equal to the pressure outside the balloon. That's when the volume actually stops expanding. So we need to account for that. We need to talk about that in here. So P in is greater than P out. And then since the balloon is a flexible, this is really important because in our inflexible system, this wouldn't happen. So since our balloon is flexible, P in is going to push. Remember, it doesn't get sucked out, it doesn't get pulled out, it's always a push, and it always moves high to low. So the greater pressure is always going to move towards the higher pressure. So P in is going to push on the balloon, increasing the volume until P in is equal to P out. Okay? Now, what haven't we taken into account? So let's go back up and see. We've now done some volume. We've got our temperature and collisions. So what have we not done yet? What variable are we missing? Take a look. Which one are we missing? Moles. So let's go down. If we have a nice closed system, our moles are going to stay the same. So moles are going to stay the same. And it's kind of good to make a point here. Pressure changes and then goes back to being equal. So I want to say that overall, pressure remains constant. Even though it had a change in the middle, the volume is what ended up changing overall in the end, where our pressure went back to being the same. So it increased its volume in order to change its pressure to be the same as the pressure was on the outside. Okay, this is where we are going to stop for today, and then we will do some more work with